We just use the fact that the force due to gravity is constant on any object in the gravitational field. We never called it a field before because the gravitational field is kind of uninteresting, especially near the surface of the Earth. It just points straight down and it has a value of g. Here I could put a little vector arrow on it, equals 9.8 meters per second squared. And the vector there means it does point somewhere, and you know where it points. It points straight down. And we use that fact that this is a constant field, and we did a little bit of derivation at some point along the way, and we found here that now E is constant, E being the energy here, and it's got two parts. It's got potential plus kinetic, and those two are constant. So when we started off with no kinetic energy up here, we released it from rest, no velocity. The potential up here was mgh. That got converted to the kinetic energy down here, 1/2 mv squared, and we solved the problem with that. How's that similar to the situation over here where we have an electric field between two parallel plates, charged plates? Now we've shown and we know that what is it about the electric field here? And here I'm going to use E for the electric field. A little confusing, we're using E for energy and electric field, but what's the deal here? It's constant. It's constant between the plates, and actually we know what the magnitude of it is. It's 4 pi k q, where q is the charge on the plates over the area of the plates. Here, right, this is plus q charge, this is minus q charge. So here the electric field is constant down there, and remember the force on any particle, so if I put some other particle here, q plus, the force on that q plus is going to be equal to what? It's going to be equal to its value, q plus times the electric field, and that's going to be constant. There'll be a constant force. Here you can see what is here, we're calling it Fe. Just move the charge that's going to fill the electric field over here onto this side of the equation, and you get the force on it. So it's going to completely identical situation over here, right? Move the mass over here to this side and you'll feel the gravitational force on this guy. So we have a very much, we can't say equivalent situation, but we have a constant force field. And in a constant force field, energy is also going to be conserved. So we're going to be able to use that. Ha-ha! What happens when you release a charged particle free to move in a constant electric force field created by charged parallel plates? I think you know! Kapow, there it goes. That's for sure. Well, it's so massive. What if we make it less massive? Woo, look at it go! How much less massive can it be? Oh, wow, it really goes. Okay. Well, we can see it does, the acceleration definitely does depend on the mass. Let's use what we know to figure out what the speed is when it crosses the plates. Our job is to find the speed of the dust particle when it's zipped between those plates. It starts at the top plate and zips down to the bottom plate, like we saw. And we're also going to have to figure out whether we need to include gravity in this problem. Is it important? Alright, so let's see what's going on here. Well, they're showing the arrow of this thing getting pushed up, right? It's getting pushed up through this electric field here, which we're given the value of the electric field is 150 newtons per coulomb. The work done by, say, the little finger that pushes the particle up through that field, right? Because the finger has to do work against the field, and the work it does against the field will be negative, but that will become positive work when we let the particle go, and then the field will do positive work. So let's just consider that positive work, which will be the force of the field times the distance it goes, which is just d, the distance between the plates. What's the force? The force is equal to the electric field times the charge, which here I'm just going to call, okay, so that's Q plus, but later on I'm just going to call it Q, and then here we have the distance. And remember, that work becomes kinetic energy on the way back down, and here, since it starts from rest, it has no kinetic energy in the beginning, that will just become the 1/2 mv squared at the bottom. Okay, so here I've just basically solved the problem, but I want to go through a little more carefully, step by step here, see what we got going on, and we'll do our comparison with gravity. So remember, for our box in gravity here, and we're also considering now that this particle is in a gravitational field, orientated, just like we have shown, right? So gravity's pointing down everywhere. But let's say go back to this box here. So remember the energy, and here we're going to have to just live with the fact that I'm using E for energy and for electric field. But the energy, any old place here, is equal to the gravitational potential, I'll call it UG, plus the kinetic energy at any position y here. So let's say if this is here, I'm going to define this to be y going up. That's y. So at any old height y right here, let's say this is just some height y right here, that'll be mgy plus 1/2 mv squared all the time. And this was just when only gravity was in the picture. Yeah, so if down here is where y is equal to 0, down here, then what would the energy be down here? The energy would down in the bottom would just be 1/2 mv squared, because y is equal to 0. What about the energy at the top? The energy at the top would just be equal to mgh, because we released it from rest. Yeah, and anywhere in between, the energy sums up to mgy plus 1/2 mv squared. So if you know that you released it from rest up here, you know the height, you can figure out how fast it's going at the bottom, or how fast it is anywhere along the way, if you know the position along the way. Okay, so that's great. So now what about over in this case? So for gravity, the gravitational potential anywhere along the way for a mass here, UG is equal to mgy. Mg is the force of gravity times the position y, the distance above the 0. And so since gravity is a constant force, the electric field is a constant force, we can state the fact that there'll be electric potential associated with this electric field, which will be, just get it the same way, the electric force, Fe, times the position where you are in the field. Y is your arbitrary position anywhere you like. At the top, what will y be? D. At the bottom, what will y be? 0. So, if we want to just talk about the conservation of energy, including the electric field, what will we have? And here I'm going to use the script E just to differentiate it from the electric field E over here. So if we're including the electric field, we'll have UE plus we'll have UG, and plus we'll have the kinetic energy, K, 1/2 mv squared. So now we got both of these guys living here, because there's a gravitational field here and there's an electric field here. Great. Now let's compare the two, right? So I know what the potential is at the top here if I know the height. In this case, the height is equal to the distance d is equal to the plate separation, and we're being told what that is right here, a millimeter, or 10 to the minus 3 meters is the separation between the plates. Gravity we know all about. Okay, so what's this electric potential guy here, this UE? The UE is going to be the electric field force times our position. And up here we're going to be talking about the potential at the top. of the plate here before we let it go, right? We bring it up here, and now it has that potential. So that's going to be, well, just like what we had up here if we used Fe, right? It's just the same as the work going up, because that's where this stuff comes from, work energy theorem. All right, so that's going to be our charge, which I'm just going to now call Q, and times our electric field, which is E, times that distance D. And we can just put in our numbers and see what the value is. Okay, let's pause for a second to take stock of our situation. Remember, we're doing conservation of energy, which now I'm calling it script E to differentiate it from the electric field, regular E. Okay, so remember, anywhere we are in the gravitational and electric field here, and they're both acting in the space between the plates. And we're defining the bottom plate here A to be 0 and the top plate to be B. But at any position we are between the plates, the total energy will be given as the sum of the gravitational and electric potential energies plus the kinetic energies. And here I'll just write those out. So and the electric potential is the electric force at the position. So I'll just write that down in general. So it's going to be, here it's going to be Q times E times Y plus the gravitational potential, mgy, plus the kinetic energy, 1/2 mv squared. And that's constant, so that's the same everywhere, the total energy. And here, what are we doing? I'm saying that Q is equal to Q plus, the test charge. Just simplifying my life by not adding that plus in there. So, okay, that's great. So that's the case. So what about the field at B? I mean, not the field, but the energy at B. The field is constant. Both gravity and electric field is constant in this situation. So at B, what do we have? Well, the guy's not moving, right? So now his electric potential energy, QED at the top, plus gravity potential, mg, and here we're calling it d for distance versus h for height. And what about 1/2 mv squared? Well, remember we released from rest, so that's 0 right there. There's nothing. Now what about at plate A? At plate A, all the potential energy gets converted to kinetic energy, right? Y is equal to 0, so those terms are 0, and then, but this V is not 0, it's not 0 speed, it's zipping along, as 1/2 mv squared. So since E is constant, right, E is constant means E is equal to EB, that's equal to EA. So that means that this 1/2 mv squared is going to be equal to QED plus mgd. And now we can solve for the speed v, because we know what g is, we know the mass, we know everything. But before we do that, we want to see, do we even need to bother to include gravity? So we're going to want to compare what? We're going to want to compare, just block some of this off. Now it's numbers time. We're going to want to compare UE is equal to what? UG is equal to what? And that's these two terms actually. Compare those, and if this one is much bigger than this one, then we don't need to include the smaller one if it's much smaller. Or vice versa, right? Maybe we don't know right now. We're just going to plug in the numbers and see what happens. Plugging in our numbers, we calculate the electric potential. Here's the charge, 10 to the minus 6 coulombs, times the electric field, 150 newtons per coulomb, times plate spacing. A millimeter is 10 to the minus 3 meters. So we got coulomb cancels with coulombs. Newtons times meters as force through a distance as energy, joules. So just combining, I have 150 times 10 to the minus 9 joules. Gravitational potential, mgh or mgd here. A microgram, 10 to the minus 6 grams, but in SI units we want to go to kilograms. It's even smaller, so that's 10 to the minus 9 kilograms times gravity is 9.8 meters per second squared times, again, the plate spacing, a millimeter. Here we have kilograms times meters squared per second squared. That's the same as units of mv squared, which is energy. Again, it's joules. And here it's 9.8 times 10 to the minus 12. So what's that? That's like 4 orders of magnitude smaller than this. So can we ignore gravity when it's 4 orders of magnitude smaller? I would say we absolutely can, and that's typically the case when we're talking about charged particles. So now our job will just be to find out how fast it's going from right here. So we're going to be ignoring that term. And then we're going to have 1/2 mv squared equal to QED. And here we know what that is. The QED is 150 times 10 to the minus 9 joules. We'll solve for that. I'll have our answer. You should check me on this. So just solve for the velocity or speed right here in this equation. Just isolate it, and I get it over here, 2 QED over m square root. QED we already figured out is 150 nanojoules divided by a nano kilogram. So that's going to be square root 300, and I got 17.3 meters per second.